So here's something kind of cool. A while back, I found a video from Tom Scott where he visited a railroad in Germany. Now, at this railroad, they used a physical model railroad to train switch technicians in order to train them to actually control points and signals on an actual railroad line. Now, this in and of itself is kind of an interesting concept. Obviously, training people with a physical model is a very unique approach. But what caught my attention was not the model, it was the actual interlocking mechanisms that they used to control the points, or more specifically, how the interlocking points were actually used.
So
you have to take it and turn it around. Just to the lower position,
Yeah. And
it's turning over there.
Okay.
We have what we call a root locking.
Do I pull up, down?
Down, please.
What happens if I were to pull the wrong lever? Just
try it.
Okay.
Try it. It won't work.
Oh.
It's closed.
It's a physical lock.
Yeah.
Now, I was aware of switch and signal interlocking systems. This was a concept that I was vaguely aware with. But as far as the actual details for how these things actually worked and how they were supposed to be used, that was never totally clear to me. That is until I saw this video where they demonstrated how a signalman would actually select the points as well as the signals that needed to be set or reset in a particular configuration to get a train from one point to another, and only when that specific combinations of signals and points was set could the signalman actually lock that configuration into place, and only then would the signals actually be sent out to the line. Now, two things that were interesting about this that I had noticed. One was the fact that no signals were actually set until all the points and all of the signals were set in advance. And then once they were, the signalman could then lock that configuration in place. And only then would the signals actually be set and the train could then be set off. The second thing I noticed is once that configuration was set in place, the levers on the interlocking system could not move, meaning that the signalman couldn't then start configuring the line for another switch configuration or different signals for when another train was to come along. Basically, the train had to clear the line first before switches and signals could actually change, which makes sense. You wouldn't want to be throwing points while a train was actually passing over it. That's how you cause derailments. Of course, now that I've got an understanding of a slightly complex system and how it potentially works, I of course had to see if I could build something like this for myself. So I decided to open up Minecraft and build just a very basic junction setup. Nothing complex, it's just a single junction with 3 lines going in. Since Minecraft switches can actually have trains going in multiple directions down either side, technically this means that I have 6 paths available. But then what I did was I gave this setup 6 different signals to indicate the 6 different paths, and then hooked that all up to an interlocking system. Again, there's no practical purpose for this. I'm not actually planning on building a switch and signal interlock system in like Minecraft or anything like that. This is just a curiosity project, just something that I wanted to see if I could do, merely for the purpose of gaining a better and clearer, more detailed understanding of how these interlocking systems work. So we'll kind of go over the theory of operation here in a second, but first I just want to show you this in action here because it is kind of cool. So the first thing that I demonstrate here is actually setting up a path. In this case, what you want to do is you want to select what direction the point is in. Since there's only one point, there's only 2 settings. And then what you want to do is select which signal actually gets to be turned on. These signals then indicate which train gets to go and in which direction they're going. Now, the junctions will actually turn, as you can see, once you select the button there. But the signals will not actually turn on until you set the signals with this button here. Once you do that, you can see none of the switch and signal inputs can actually be changed. They are locked out. And this will remain the case until the user turns off or resets the signals, at which point all the signals turn off. Now the signals and the points can be changed. Now, that particular behavior isn't too terribly complex to wrap your head around. The complexity comes when you want to make sure that the user cannot accidentally select 2 valid paths at the same time. As you can see here with the junction reset, we can select either signal 2 or signal 3, since these are both valid paths. And if we select either one, we can actually lock that in place. That is a valid path. The interlocking system will allow for that. But if we try to select both at the same time, what this will do is signal two trains to go in opposite directions on the same track. Not a good idea, so the interlocking system does not allow that, as you can see here. Likewise, if we try to select a path with the junction set in a direction that does not physically allow for it, the interlocking system automatically recognizes that this would cause problems, this would cause derailments, or it would just send a track in the wrong direction, which is obviously against the intended purpose of this system here. So again, it locks the user out. The user is not able to set any signals as a result of this. No signal set means no trains can move. And then, as I stated earlier, you wouldn't want the user to change signals and switches as the trains were passing through. Now, in order to actually prevent this sort of thing, you would need sort of a block detection system. Obviously, there's no good way of detecting when a train is present in a block in Minecraft. That's kind of just a shortcoming of the minecart system. No big deal. I've basically just substituted it with a single lever. So with the lever up, or the lever down, I should say, and that signal on, that signals that all blocks are clear and there are no trains currently passing through this junction. If it's down, however, up, if it's up and the signal is off, this means that there is a train present. And so long as that signal is off and the train is present, it locks the user out again. The user is not able to retract any sort of signal or switch settings, which means they are then unable to change the switch and signal settings. Again, this is just a little safety system set in place so that if there is, in fact, a train moving through the junction, the user is physically not able to retract any sort of settings, change signals, change switches, because again, that would be a bad idea. That would cause derailments. Now, let's look at theory of operation, because this is actually a very interesting set of circuitry to control all of this. There's room for improvement, of course, and obviously, if I'm going to be doing more complex junction configurations, this sort of system may not work. This is just an initial prototype to kind of get the idea of how this sort of system would probably be set up. I will probably be doing more complex junctions in the future just to kind of test myself, but for the time being, this is a very basic setup, very basic, first steps to creating this sort of system. So I think as far as the first attempt is concerned, this is actually pretty decent system. But the way this works is fairly simple. Obviously, if you were to look at the actual switch controls, what they are basically these really big throw switches, these big levers. And the way that the user gets locked out of them is they get physically locked out. Once the system is in an interlocked state, those levers cannot move. And if we were to think of this from a digital logic circuit's perspective, what we're effectively dealing with is essentially like a D flip-flop or a T flip-flop, in this case a T flip-flop, with a gated input, just something that allows the input to be disabled when we don't want a signal to be going through. So we have our 7 T flip-flops here, 8 if we include the one that actually sets the signals, but we'll disregard that for the time being here. But we have 7 T flip-flops, and those control either the point or one of the 6 signals. Now, of course, we can turn them on and off. That's perfectly fine, but we don't actually want that signal going through. We want to kind of try and control when those signals go through, because if we turn on and off signals while they're actually affecting the physical signals on the track, a train might end up getting a green light when it's not supposed to while we're still configuring everything. That can be a bad thing. So we have this 8th T flip-flop here. This is the set signals T flip-flop. You can kind of consider this as like the last lever that the operator has to flip in order to actually send the signals down to the tracks. And so long as this is turned off, no signal will actually get through. Now, what makes this an interlock is so long as this signal is off, no signal can get through, but we are allowed to change the state of the other T flip-flops, and that's because the enable signal for all of these is on. But as soon as we set the set signal line to on, the signals from these T flip-flops are allowed to pass through to the junctions and to the signals, but the enable line is also turned off, which means the user is no longer able to change them. And this basically ensures that the user is not able to change the signals while they're being sent down to the line, but also if the user is able to change the signals, they are not being sent down to the line. This is just sort of a safety thing. Now, that all works perfectly well, but of course we want to make sure that the user can't select a combination of signals and switch configurations that is invalid. If we're sending a train down a specific line, we want to make sure that the appropriate signals and switches are thrown correctly. We don't want multiple signals to be turned on. That would be a bad idea. We don't want a signal to be turned on if the switch is thrown in the wrong direction. That would also be a bad idea. So connected to the outputs of these T flip-flops again, is just a small decoder, and what this decoder does is it encodes all of the valid paths that a train can take through this junction. Since again there's 3 tracks and the train can go in 2 directions in each track, there's 6 valid paths that a train can take, so there's 6 lines in my decoder. This decoder, if it detects one of 6 valid combinations of switch and signal settings, it will send a signal back towards the set signal enable line. And this again is just another layer of the interlock here. What this basically means is the user is not able to set the signals on the track until they've selected a valid combination of switches and signals. Once they have selected a valid combination, they are then able to set the signals on the track, and at that point they're no longer able to change them. Combined with this signal, of course, is the signal that indicates when the blocks are clear. This is just ANDed with this signal, so only when the user has selected a valid track and the blocks are clear can we actually change the settings of the set signal line. If there is an invalid track selected or the block is occupied, we are not able to change that state. And that just, again, makes sure that, one, the user can't push an invalid combination of junctions and signals, but also, two, the user can't retract the settings and unlock the interlock while there's still a train in the junction. So again, that's basically everything. It's not a terribly complex system. It's fairly simple, but again, this is an interlock system that's controlling a very simple track. Again, I do plan on eventually, at some point, building something a little bit more complex just to try and test myself a little bit. But for the time being, this is a pretty good first step. For future iterations, though, I think I'd probably take a different approach. This system right here, where you have to manually select the junctions and the signal settings, and then the interlock will basically not work unless you select everything correctly. This is fine in concept, but I understand that this sort of system is not how they do things anymore. Nowadays, they usually have an in-out system where they select where they want the train to come from and where they want it to go, and the computer kind of sets all the signals and switches accordingly. In that case, the only purpose of the interlock system is just to make sure that the user can't select 2 paths that overlap or cross over each other. This, of course, begs the question, if that's how we do it nowadays, why did we have the system way back when where we had to manually set all the signals and switches? I don't really know myself. I'm not that big of a rail fan where I would have that information, but if I had to guess, it's probably because being able to automatically control the state of switches and signals would have required a motor or some kind of a power system to drive those things. And my guess is that cheap, readily available, mass-produced power systems to control these things probably weren't available when these systems were being set up. So a lot of this stuff probably relied on muscle, meaning a person needed to be able to move a very, very big lever to move all these switches into the correct position. And then the interlock was just there to make sure that the operator did everything right. The interlock didn't actually set all the switches, they were just a safety measure in place. Of course, nowadays we have motors, we have pneumatic lines and things like this. We can actually automate a lot of these things. So nowadays we just have to select the path, and then the interlock is just there to make sure that, again, 2 paths aren't selected at the same time that accidentally cross over. So if I'm going to do this again, I'm probably going to change the interface to where the user selects paths rather than signals and junctions. But again, that's going to be a little bit later down the line. For the time being, again, I think this is a good exercise, and it was really just a fun small project that I got to put together. But anyway, that was what I ended up working on. That was what I ended up learning as a result of it, and I figured that was something worth sharing. So hopefully you enjoyed, and yeah, we'll see you in the next video.